Hello, this is test. Hello, this is Professor Todd Elliott, and in this presentation we will examine using a BJT transistor as an on-off switch to switch a relay coil, which is a very popular application in industry. Transistors can be used to drive solenoids, relays, lighting, all sorts of different things. So you may not see a circuit exactly like this. Nevertheless, the principles and the general context is perfectly valid. Okay, look at the original circuit, and this is sort of in its natural de-energized at-rest state, and we'll use that as the starting point. Okay, so what do we see here? We see transistor Q1, which has its base current controlled by this simple toggle switch. The collector of Q1 ties via R4 into the base of Q2. So Q1, as we'll see in the upcoming slides, is used to control the base current of Q2, and ultimately Q2 here, right, when it turns on, provides a current path through this control relay coil, which can control that contact. So anyway, that's the general overview. We'll get into details on the next slide. Okay, so in this case, with the switch open, the relay is energized. And why is that? Well, if you just simply look at it, you can see then if the switch is open, there's no base voltage going to the base of Q1. Therefore, there is no current to the base of Q1. If there's no base current, then there's no collector current. So we can say then that transistor Q1 therefore must be in cutoff. So with transistor Q1 essentially acting like an open switch, you're ignoring the cutoff leakage current. Do you see that from the 12-volt power supply E, follow the arrows here, we have a current path down like that. So the transistor Q2 has sufficient base current to forward bias it, so therefore Q2 is turned on. And there's the formula for solving for the base current. So the idea is to use Q1 and Q2 as on-off switches. And in this case, with the control switch in the open position, we just saw that Q1 has no base current, so it's in cutoff. Q2 has plenty of base current, so it's going to be saturated. And therefore, then, because it's saturated, it is essentially pulling its collector down to ground. Okay? And we are assuming that the collector to emitter voltage on Q2 is 0. We know from earlier discussions that when it's saturated, you're not going to get it down below 0.1, 0.2, 0.3, something in there. But in any way, virtually all of the 12 volts appears across that relay coil. Okay, so it'll probably be like 11.99, right? And small bit for this Q2 saturation voltage. But anyway, relay coil CR1 is energized. And note that that normally open contact is now being held closed. The diode here, notice the polarity right there is the cathode. This is the positive point. It is reverse biased, and we'll see shortly why that diode is there. But right now it's reverse biased. It's not conducting current. Okay, so anyway, this is just a little different picture. I showed some typical meter readings. You can see here with this open, the base voltage here, VB, is essentially floating. So this is less than half a volt, so that's essentially zero. Okay, and our current path is down like this. We know that the base to emitter junction is working, okay, because that's totally normal. And again, this is the Q2 saturation voltage. Note, in a practical transistor, you're never going to make that zero. So that's right in the expected range of 0.1, 0.3 if it's fully saturated. And there is a current path then going from here, like there, down, and then back, just like that. Okay. All right, and of course that's being held closed. Right. So the relay coil is energized via Q2 being saturated. This one here is in cutoff. Okay, now we're going to close the switch. Okay, so with the switch closed, a little different story is now we have a current path down like here and down and back. So that means then Q1 is saturated. With Q1 being saturated, ideally it's pulling point VA down to ground. In reality, it's going to be, a little bit above that because of the Q1 saturation voltage. But in any way, the current path is down this way, and there's going to be no current flowing through the base here. So therefore, this is off. Of course, the coil is de-energized, and the contact is in its normal rest position. So, okay, so can have a look at that. That's all the important stuff. Last thing here is that with the freewheeling, this is called a freewheeling or a snubber diode typically, right? Its purpose there is when we open the switch, so we would that the as you saw on the previous slide, the coil is going to be energized. When we close it, the coil is going to be cut off. That stored electromagnetic energy needs to be dissipated, needs to go somewhere. So therefore, then we know by Lenz's law, when that field collapses, it will flip reverse polarity, and therefore we have a current path down like that to bleed off the energy from the coil through that power diode. If we were to leave that diode off, what would surely happen is that high discharge voltage would destroy the collector junction of Q2. So this is a common feature whenever using any type of transistor to control anything electromagnetic, solenoid or relay or whatever, to protect that transistor. And again, that's typically called a freewheeling or a snubber diode. Okay, again, here I just have the simulation, and you can see then with that switch closed, okay, this VB is the base to emitter junction. Just look where the meter is. Okay, that's, typically your 0.7-ish. Okay, this is pulling VA down to ground, but it can't really be ground because of the saturation voltage. But again, I said if it's fully saturated, it's in the 0.1 to 0.3, and it's right in that range. So therefore, then there's no current here. The base to emitter junction has not reached the 0.7 threshold. It's 140 millivolts. Okay, so Q2 will be in cutoff. So therefore, there's no coil current, and therefore that's back into its rest position. Okay, so let's do a little bit of troubleshooting. Transistor Q1, base to collector short. All right, so with Q1, the base to the collector short. How do we know that? Look at this meter, right? This meter here is measuring the base voltage, VB, right? VA is from the collector to the ground. So essentially we have the 690 millivolts, right? So we can say here that VB equals VA equals, so therefore, because this is exactly the same as that, then therefore internally it's shorted between the base and the collector, and therefore because of that, that transistor is faulty. Look over here. Okay, the base 2 meter voltage is not sufficient to turn on Q2, so you need to be closer to the 0.7 volts. We're getting, it's almost there, but not quite there, right? We know that Q2 is off. Look at this, right? This is virtually at 12 volts, right? So this is at 12, right? So this is going to be, the voltage right here is going to be the 12 minus the 11.79, just call it 8. So this is going to be like, something like that, which is obviously not enough. It's 12 volt coil. That there is telling us that this transistor is in cutoff. It's not conducting any current. Okay. Transistor Q1, base to emitter short. Okay, so this is the base, and then this is the emitter, like that, and we're saying it's shorted. Now look at this. This is showing picovolts. Now this is a 80s multisim for this. Okay, so it's a software simulator. It's generally actually quite good. But in the real world, your meter's not going to go. Typical multimeter will not go down that low. But I mean, can we just call that this, for all practical purposes, 0 volts? And because of that, it's pretty clear that the base to emitter is internally shorted. And then because of that, then the transistor Q1, obviously it's not going to be working. Okay, so it can't turn on, so Q1 is in cutoff. We know that because VBE is basically 0, and that's going to allow, again, a current path down like that. So Q2 is saturated. Look at the base voltage at Q2. Relay coil is energized. Okay. Transistor Q1, open base to emitter, right? Default is base to emitter open. Okay, so this is the base, and this is the emitter. Okay. Look at this voltage here. Okay, it's almost 11 volts. If with the switch closed, we expect VB to be 0.7-ish. Okay, it's much higher than that. So therefore, we know that the current is not going into the base there. If the emitter was open itself, we get basically a very similar result. So sometimes faults have more than one cause, but in any case, the transistor needs to be replaced. So it's really not, practically, it's really not necessary to determine like the exact precise fault. Just determine the faulty component and just replace it. So with no current going into the base of Q1 is therefore is in cutoff. Okay, and again, right, we have our current path down that way, turning on Q2, and we know Q2 is saturated because of the near 0 collector voltage, which of course then completely energizes relay coil CR and closes this contact. Okay, move on to transistor Q2, base to emitter open. Base Q1 is in cutoff. Okay, so this Q2, so base to emitter open. Okay, our switch is open here, so current should be able to go down like this. Okay, we've seen that before with that open, Q2 should be able to turn on, but in this case, because of the base 2. I thought I had that wrong. Base to emitter. Then there's no path going down through there, right? Hence that voltage is nearly equal to the supply voltage. So Q2 is definitely off. We know Q2 is not conducting because of that. So therefore we know that there's no current flowing that way. Q2, collector open. This one is Q2 collector. And there's no magic to this. It's just basics. You have to know how it's supposed to work before you can troubleshoot it. There's nothing magical about it. Sometimes for real circuits, you need to you need to isolate, unsolder, just connect things to to sort out the fault. But you just kind of go with an understanding of how the system, regardless of its complexity, how it's supposed to work. It always breaks down to fundamentals, and just troubleshoot it from there. So there's techniques you can learn, but there's nothing magical because every situation is different. Sorry, collector open right there. Okay, again, okay, look at this. Okay, this voltage here is essentially 0, and we sort of expect that because we have that switch to be open, so that means the base voltage here is essentially floating, which is fine. Current then, if everything is working properly, should be able to flow like that through the forward biased base to emitter, right? And so this value here looks normal. So this voltage here should ideally be 0, right? Take a look at it. It's nearly the supply voltage. So the base to emitter junction is working, but obviously current is not flowing through the collector because it's open. Okay, so. Okay, transistor Q2, collector to emitter short. So collector to emitter short. Just look at this. Again, this is a simulation. It's showing, 0.048 nanovolts. Okay, that's 0 volts. Okay, that means then there's a short internally between there to make that voltage that low. Okay, so that's about it really. Have a look at this. Just take it one step at a time. I've tried to put on as many notes as possible. So anyway, thanks for watching, and we'll talk to you later. Okay, bye.